how to derive rate laws from experimental data. So I'm going to keep my promise. So we're going to do that today. And the first thing that we have to do, I'm going to give you kind of hints and clues of things to look for when you're looking at data. Okay, this is obviously one that's a pretty simple one to start with. Okay, first thing you want to do is know what we're looking for. Okay, we are trying to derive our rate law. So remember, rate equals K, which we haven't talked a whole lot about, but that's a constant. So you're going to learn to actually solve for it today too. Okay, and then it's times the concentration of what? Of our products, reactants, products over reactants, what is it? Times concentration of only the reactants, whatever they are. Okay, here we have two reactants on the left-hand side. Okay, so we have A, and then I'm going to put an X here because what we're finding is the order. Okay, you've been given, last week when we talked through this, we were given this number. Okay, that order is to what magnitude or what extent does that concentration have on the effect of the rate. Okay. And then we have B, and I'm going to put it to the Y because we don't know that. Okay, it's not given to us. So we're going to take this data and we're going to find the orders. We're going to find X and Y. Okay, that's the whole point of this. As I said, those numbers here do not come from the equation. Okay, they don't come from the moles in the equation. We have to decipher data to find those numbers, to find those orders. Okay? First things first, what you're going to do, so we have A, B, and C. Eventually, especially on the homework, I will actually put in compounds, okay, but we're just trying to get the general idea. First thing you want to do is you want to look at, okay, here's the number of trials, so there's 3 experiments done, okay. You're going to look at the concentration, so this is of A, you got to read the table here, and this is of B, okay. And these are the rates, okay, at each of those concentrations, okay. The first thing you want to do is you're going to need to compare 2 experiments. It may be 1 and 2, or it may be 1 and 3, okay. But we're going to start by first trying to find the order for A, just because it's first, okay. So what you want to do is you want to find 2 experiments. Okay, this is key. Everybody listen up. Okay. Find 2 experiments where A changes, the concentration changes, but B does not. Okay. If you pick 2 experiments where A and B both change, you don't have a control. Okay. So you can't compare those because you don't know to which one did the rate rise. Okay. All right. So look at this. Try to find that. Find 2 experiments where A changes and B does not. Anybody find one? Okay. Anybody find it? Okay. All right, that leads to something else. Okay, so with this example, did you find that anywhere? Okay. That's what you're going to do anyways first. Sometimes you will find that happen. Something in my eye. Okay. So if you don't have that, okay, then something else is going on. Okay, so what you're going to do is you're going to look over here and you're going to see, okay, I have a situation where in experiment 1 and 3, the rate stays the same. Okay? So if we look over here, for 1 and 3, A is the same, right? So you would imagine that it wouldn't change the rate. But what happened here for B, 1 and 3? It changed, but the rate didn't. So what does that mean about B? Does it have an effect on the rate? No, right? Because it changed, right? Okay. and the rate did not. Okay. All right, so first we looked for, okay, you can do these either way. I just wanted you to see that. Okay, you can do this either way. You can look for rates that are the same and then try to go over and see if you have one that's to the 0 power. Okay. You may or may not have a 0 order. Okay. These are all just different depending on the reaction. Okay, but from this, so I'm going to move over here so I can write. Okay, here's the data. It's still there. Okay. So this is what I know at this point. Okay, does everybody see how B is to the 0 power? I'll go over it again. Raise your hand if you don't. Okay, you don't? Okay. If you look up here, I just moved the data. Okay, if you look at B, look at experiment 1 and 3 for concentration of B. Okay. For experiment 1 and 3, the concentration changed, right? Okay, but what happened to the rate? It didn't. So it doesn't matter if you were to increase B more and more and more, the rate didn't change, so it didn't have an effect. Okay, so what we know right now is rate equals K times A to the X times B to the 0. Okay, if B doesn't play a part, has no effect, then we can just kind of not worried about it. It's not going to affect A. Okay. All right, now we have to find X, right? We have to find the order of A. So that's what we're going to do. We're trying to find X. Okay. So what we're going to do is we're going to set up a little ratio here. Okay. It doesn't matter which experiments I use at this point. You're going to get the same answer. But why I told you that in the beginning is because normally, if this wasn't 0 order, you have to find an experiment where A changes but the others don't change. Okay, because otherwise you get mixed results if you don't do that. Okay, I'm just going to use 1 and 2. So I'm going to take 0.10, okay, and 0.20. Okay, I got that from right here and right here. I'm in front of the screen, sorry. Okay. Key thing, I haven't written it in yet because this is the most forgotten. We are trying to find X, right? So you need to put that right here. Let's circle it. Okay, that's what we're looking for. Now all you do is match these concentrations with the rate. Okay? So here it's 2.0 times 10 to the negative 4 and 4.0 times 10 to the negative 4. Okay? And that's molarity per second. So second is our time unit here. Okay? So when we take 0.10 and divide it by 0.20, we get 1/2 to the X, don't forget that X, equals 1/2. So if you divide those two, you get 0.5 or 1/2 there. Okay. So X is equal to what? 1/2 to the what power equals 1/2? X equals 1, exactly. So it is first order. Okay, so how we would say this? We would say this reaction is first order with respect to A and 0 order with respect to B. It is first order overall. Well, here not really because you have no change. You want to change. See how it was 0.1 and 0.1? So you need some kind of a change there. So it was held constant at 3. So, okay. Last thing we have to do, we're almost done, but we have to find K. Okay. All you're going to do is go to one of your experiments. Always go to the first one just because that's the first one there and that's just what I do. Okay, and I use that data in that experiment to solve for K. Okay. I'm going to run out of room here. Okay, if we rearrange to solve for K, K is going to be equal to rate divided by the concentration of A. Hang on, let me rewrite that. It's not going to let me. We don't have to carry the B. It's to the 0 power, so we don't have to put that in here. Okay? If it was to the first power, then you would. All right, now go up to the first experiment. What was the rate? 2.0 times 10 to the negative 4th. All right, what was the concentration of A? Asleep this morning. 0.10, right? And that's to the first power because we found that. All right. Put that in your calculator. Dividing by 0.1 basically. So you're going to get 2.0 times 10 to the negative 3. The only thing now is we have to put our units here. So we have units, and there's a trick to this. This one's easy because you just have this first power. But if you are to have to the 4th power, and to the 3rd power, and to the 2nd power, then it gets a little confusing how your units cancel. So there is just a little shortcut that I use, and it works every time. Okay, so I'm going to show you this. Okay, we've found K. We just want to find the units. Okay, the units are always going to be 1. Okay, divided by, and then we're in seconds, of course, but okay, here. Okay, M is for molarity. Okay, I'll explain this in a second. Okay, it's reciprocal time here. I'll show you a couple ways you can write it. What you're going to do is take the overall order. N is equal to the overall order. Okay. What's the overall order for this reaction? Like I said, it's simple. So you get 0, right? So if you get 0, then you just leave out the molarity part. Okay, and so you would end up with 1 over S, reciprocal of seconds. You can also write this, that's the same as writing S to the negative 1. It is. You take 1 minus 1, sorry. Yeah, that's always, it just works that way. So you take the overall order minus 1, and if it's 0, which a lot of times it's not going to be 0, we just happen to have only one order. Okay? But that's just a shortcut. Instead of trying, you can cancel out all your units and do all that if you want to. This is just a shortcut. Okay, so final answer, erase all this. So this is the final answer that you would report. You have to put in everything that we have found or that we know. Rate equals 2.0 times 10 to the negative third 1 over S times the concentration of A to the first power B to the 0. It's understood if you leave B off that I know it's to the 0 power, so you'll see it either way. So you put in your K, and then what we found was the 1 and the 0. You have to put it in, rates equal to K times the concentration. Well, you just found K, so now you put it in your final equation, or final rate law expression.
Okay, all right, got it.
Whoops. How does it do that? I don't know what the deal is. Okay, you have A, B, and C. Okay, so same directions. I'll write out the equation here. Okay, doesn't really matter what the moles were. I think it was 2A. I don't remember, but we're not too worried about that. Okay, so this time we have 3 reactants. Okay, so first thing you want to do is look at your data. Start looking at it and seeing if there's, so you may want to first look for if anything is 0 order. Okay. See if you can find anything that would be 0 order in this data. Tina thought C. Anybody agree with that? You think C is 0 order? Okay. Okay, if you look at 1 and 3, same rate, right? Okay, so that's an indication that there's probably one of these that's 0 order. So if you go over and so even if you started over here, at 1 and 3, A doesn't change. So it makes sense that the rate wouldn't change. Same for B. It's 0.1 and 0.1. So would make sense. It's the same. But for C, experiment 1 goes from 0.1 to 0.3. It changed, but the rate didn't. Meaning the concentration went up. So if it was dependent on rate, then it would have sped up the reaction. But we see here that the rate's the same. Okay, so this would be 0 order for, so right now we know this. We know rate equals K, it's the concentration of A to the X, B to the Y, and C to the 0. Okay, so that may be the first thing that you want to do. Look for if anything is 0 order. Okay, and like I said, there's not always going to be a 0 order, but okay, so what I do if it's 0 order, I just cross it out because it doesn't really, not going to help me with anything else. Okay.
So if there's a table with several experiments and you find one of them that does that in just a couple experiments, you can just mark it out?
Yep, if there's more than one. So say B was also had changed, but the rate didn't, then you could mark it out too. All right. Now you've got to find, so we're going to find the concentration, or excuse me, the order of A first. You can do it B first, doesn't really matter. Okay, we're just going to start with A. So you need to look for an experiment, 2 experiments, where A changes, but B does not change. That's the key. Okay, if people mix up experiments, and you end up getting, like I said, conflicting results. Somebody like 2 and 4? Anybody else? Agree? Okay. And let's do that. Experiment 2 and 4. We're going to look for the order of A. It's going to be equal to, set up my little ratio here. Okay. She said 2, right? So experiment 2 is 0.20. Of course, this is molarity, but you don't have to. Okay. And then 4 is 0.60. Okay. Sometimes there will be more than one scenario. Sometimes you can use, 2 different experiments. It'll still work. Okay. If we go over from 0.20, we have a rate of 6.0 times 10 to the negative 4. And 1.8 times 10 to the negative 3. Okay, because we're looking for x of A. Experiment 2 and 4 for A, it changes. But the but the concentration of B does not. Okay. It's 0.3 and 0.3. If they both change, then you're not getting the effect of which one. You've got to you're mixing them. Okay? End up with basically 1/3 x is equal to 1/3. So x equals 1 again. And they're not all going to equal 1, right? So there's going to be ones that are different. One common mistake, I forget which one it is, but remember this is an exponent. Okay, so if you have, which one is it? Equals, okay, so what if this had said 1/9? What would x equal? 2, not 3. Okay, it's an exponent. So if this had said 1/9, okay, a lot of students will put a 3 there because 3 times 3 equals 9, but this is an exponent. 1/3 to the second power equals, that's a very, very common mistake on the exam. And you'll have ones like that when we do your homework and practice. So. Okay, B. Probably going to run out of room, but we'll try. Okay, now we have to pick 2 experiments. Now we want B to change and A to not change. I have a line through this. Let me clear that up. One and 2. Is everybody good with that one? Okay, it's the most obvious one. All right, so let's plug it in. We've got 0.10 over 0.30 to the y. Like I said, I'm going to run out of room. Hang on. I have to rewrite all this. So I end up with y equals 1. So I end up with 1 again. Right? So we've got A to the first order, B to the first order, C to the 0. So it's second order overall. Everybody agree with that? Add up your orders. All right, now I want you to solve for K. Okay, so pick an experiment. When I show it, I'm going to pick the first one, but you can pick whichever one you want. Okay, you don't have to include C because it's 0 power. And solve for K, and then look back at your notes if you need to figure out the units. Solving for K. Does everybody have that written down? Got your answer? Okay, just use the data from one of the experiments. So if you use the first one, okay, so all this is just rearrange. Anybody got an answer yet? No, K is a constant. You just pick the whole experiment. Yep. So you put in your rate. I just picked the first one. Then you put in both concentrations raised to the order that you just found. And then you just solve. Answer, anybody? Seconds. Answer and units. Because it's a constant, exactly. You could pick experiment 4 if you wanted to, 2, 3, or 4, doesn't matter. Once you find the orders, yeah, but once you find the orders, that's all you need to know, and then you'll get the same answer no matter which experiment you use, exactly, because K is a constant. Anybody have an answer yet? You guys are dead today. Y'all look miserable. Do what? Okay, looks like you're off by exponents, so probably your calculator. All right, we're going to wait until somebody gives me an answer. Calculators, spring to class.
I brought the wrong one and I can't remember how to do these maths.
Yeah, you rearrange this equation. All you're doing is solving for K. You know rate, it's right here. You know A, it's up there. You know B, it's up there. You find K. You just rearrange and solve for K. Very good. Okay, and what's our units? Go back. Look at your... You're not going to get this unless you practice and be involved. Okay, very good. All right, so if we plug in 2.0 times 10 to the negative 4, so I got it from right here. And I have A right here, and I have B. So I plug in 0.2 times 0.1. Those are all to the first. K equals 0.01. Okay, for my units, my formula is 1 over molarity n minus 1, and then it's per seconds. So you look up in your table, so this may be minutes or hours, it just depends, okay, on what the data says. Okay, so n is the overall order, so what's the overall order? 2. So 2 minus 1 is 1, so 1 over m molarity per second. Then your final answer, you just plug that in. So your final, you would have rate equals 0.01, 1 over m molarity per second times the concentration of A to the first, B to the first, C to the 0. So that would be your final answer. You just want to put it all together. No, you don't plug in. You just, yeah.
Well, I brought the wrong one. I've had two. But then another one quite short. It's short person to my calculator. Maybe it's me.
All right, any other questions before this clears? Okay, most of the problems that we're going to do are going to be like those, so we'll practice those some more. There is one other exercise that you can do with this, and that is you can be given this data, but then fill in the holes. Okay? So you really just work backwards. The first thing you're going to do is find K. Okay, so you're going to look, see there's one that has to be given everything. Okay, so since we just found K, let's find K again. K is always going to be equal to rate over the concentration of, here it's A and B or whatever your reactants are. Okay. Up here, it tells you your order. So you have to be given that, right? Or you had to experimentally find it. Okay, so it says it's first order with both. Okay, so first thing I want you to do is just find K. Okay, so that's the last thing we did in the previous problem, so this is going to be the first thing you do here. And this time you can only use experiment 1 because it's the only one that has all the data there. Okay, so if you write out what you know, this is what we know. It's first order with A and first with B. We rearrange to find K. We get rate divided by A. That. Okay, so then plug in the data points and find K. So once we do that, 4.0 times 10 to the negative 3 divided by 0.2 to the first and 0.050 to the first, you should get about 0.40. And then it's second order again, so we have the same units as we did on the previous one. So molarity per seconds. Those ones were given to us in the problem on the previous slide. I've moved to this next one. All right. So what do you think we could do now that we know K, we know the orders? How do you think we can find the concentration of A? We know everything but one thing, right? So we go up here. Our rate is 1.6 times 10 to the negative 2 molarity per second equal to 0.40, 1 over M. There we go. Okay. A to the first order is what we're trying to find. And B is 0.050. So we know everything but A, right? So it's isolate your concentration of A to the first power by itself, okay, and then solve. So if you want to move everything over, so you would divide by our 0.40 second. You can rearrange this beforehand if you want to, or you can plug them in and then rearrange. Okay, it all ends up the same. So if you wanted to rearrange first, you would have this. So we know everything except for looking for a concentration of A. So we go to that experiment. You have to use the rate from that experiment that you're missing the concentration. So you get 0.4. We already found that. We're looking for A. So we rearrange. So to isolate A by itself, we have to divide through by 0.4 and 0.050 molarity. And then A is to the first power. So A is going to be 0.80. Okay, if you wanted to check your answer, how do you think you could go about doing that? If you go back up here and you take 0.40 times what you found, the 0.80, times B, the 0.050, what should your rate be? 1.6 times 10 to the negative 2. Okay. Do the same thing for B. So start back up here. Okay. And this time you're looking for B. All it is algebra, really. It's just rearranging. Once you find K and you're given everything else, you just solve for what you're missing. Did you use 0.05 instead of 0.5? So I'm looking for B. So just a different way to look at it if you're filling in for concentrations. You find K first, and then just rearrange your rate expression to solve for the concentrations. Okay, so this is important. So if you derive your rate laws, this can tell you in the lab, what's going to speed up your reaction and what's not going to speed it up. So you can do a series of trials to see, and you're going to do that in lab. I think it's maybe next week. I can't remember. Yeah. And you're going to derive your rate laws, but you're going to experimentally, so you're going to have a stopwatch, and you're going to get your speed of the reaction, the rate of the reaction, based on, a color change is what ends up happening. Okay, and so you can find these numbers and then take them and find the order of your reaction. So if one of your reactants is to the second power, it has more of an effect on the rate. So if you want to speed it up, then I would add more A, add more concentration of that reactant. Okay, so that all went with our second factor that affects rate. So you may not remember from last week, but the first one was the nature of the reactant. So we just talked about surface area, the solid, liquid, or a gas can affect the rate. And then this one's the big one. This was concentration, because we know our rate law is based on the concentration of reactant. So that's what we just went through. Okay. We've been talking about a transition state. We looked at our exothermic reactions, and we talked about that energy of activation, having to get up on top of that hill, and we have to have enough energy sufficient enough to get on top of that hill, and then the reaction will, proceed on its own. Okay, this is a transition state theory, really, so we've already been kind of talking about. But reactants form a high energy, intermediate. Okay, that's what they form first. So we have to have enough energy, to get over that transition state or that intermediate. Okay, so for a reaction to occur, the reactants have to have, like I just said that, enough energy to get up on top of that hill. Okay, that's called the EA, or the activation energy. Okay, so we talked about if we had, when we take methane and oxygen, we have to use a match to get the reaction started. And then once it's started, it's on fire, it's burning, then the reaction proceeds on its own, for quite some time. Okay, how this is related to rate is the lower that energy is, so the lower that hill is, the faster the reaction. Okay, so think about it. If you have to get all the way up a whole lot of energy to get a reaction started, it's going to be slower than if you had a little hill to get over. It's going to be faster. Okay, so there's our idea here. There's our boulder. We think about it as our reactants. It has to get up on top of that hill first, have enough energy to get there before it can proceed. Okay, and so the smaller that energy of activation, the faster the reaction. Okay, so here's another one. There's our delta G there. And now it's showing actual reactants in here. So we've got, looks like an alcohol. So we've got hydroxide and then methyl bromide. Those are our two reactants. So they have to collide, and there has to be enough energy right there then to have a transition state, and then they'll rearrange to form products, okay, if we can get over that activation barrier. All right. There's quite a bit on this in your book, so if you read it, you can thank me later that we're not going to spend a whole lot of time on this, because you can do a lot of different calculations and things with the Arrhenius equation. But all in all, it's really kind of common sense that if you increase the temperature, you have a greater fraction of molecules possessing enough energy, okay, to get over that activation barrier. Okay, so if you heat a reaction, typically it's going to proceed at a faster rate. Okay? But this is, so the Arrhenius equation, it goes through, I kind of put a little bit here. The energy of activation, R is a constant, and then the temperature, okay, and the natural logs, you have to do quite a few calculations there. But, and I wouldn't worry too much about this, but you end up seeing that this happens to a certain point. Okay, so it doesn't, you can't just increase, and it just, you know, at some point it levels off. Okay, so you can increase temperature up to a certain point, and then it's not really going to help. Okay, so but the third factor that affects rate is temperature. So it's got that number 3. So first is nature, second is concentration of reactants, and third is temperature. And we may come back and do a little more on deriving this. We'll just see what time allows, but that's the main point. Okay, and it goes through. I'll give you a little extra information there if you want it. Okay, the fourth is a catalyst. Anybody ever heard of a catalyst before? Anybody ever use one? Anybody working? Okay, what do you use? Okay, so she said peroxide is a catalyst for developers for hair color. Okay. All right, catalysts are great. They will speed up reactions. They are used, industry. We're going to look at, they're used in your cars. They're used, everywhere. Pharmaceutical industry, everything. But they can be very expensive. Okay, so that's kind of a drawback to them. For example, I used a catalyst in a research project, and the bottle was about this big. Granted, you can use a catalytic amount, so you don't have to use a whole stoichiometric amount. But I believe there was about, I think it was a 5-gram bottle. Okay, so imagine, 5 grams is not very much, especially on industrial scale. And it was about $700 for 5 grams. So yeah, it was very expensive. So we were doing a small scale reaction, so we used it, and it lasted me for, it was actually called Grubbs Catalyst. It was great for what we wanted it for. It sped up the reaction, it made our reaction more efficient, but had I been in industry and not doing a smaller scale, there's no way you would have been able to afford that. You're looking at thousands of dollars just for one step of your reaction. Okay, so they are great, but can be, you want to try to find ones that are cheap, and there are ones that are cheaper, but in pharmaceutical world, most of them are pretty expensive. The reason that catalysts are going to speed up reactions, and this is key here, I kind of get this backwards sometimes, but they are going to alternate the pathway. They change the pathway that the reaction is undergoing. And in that, they lower the energy of activation. Okay? So the catalyst provides an alternate pathway with a different activation energy. And usually that, of course, that activation energy is going to be lower. So we went from this kind of high activation energy to one that's smaller but a different pathway. Each of those are kind of different steps in the reaction. Okay. Homogeneous catalysts are popular. They're actually going to be in phase with your reaction. So they would be in your solution and act as a catalyst. There are some like peroxide. I mean, it catalyzes, that's a cheap catalyst. But a lot of them are heterogeneous, and usually these are the ones that are pretty expensive, these fine powders that are made of ruthenium or some kind of transition metal. They're going to be more expensive. But a heterogeneous catalyst, these are nice in pharmaceutical industry and in just research in general, because typically you can just filter it off. Once the reaction's done, then you can just filter it and your catalyst stays on top. And sometimes you can even reuse the catalyst. So that's nice if you can do that, especially when they're expensive. So, okay, here's a commercial catalyst. Okay, whoops. Yeah, the automobile catalytic converter system in your car. The purpose of it is to take our harmful / poisonous pollutants, okay, that are produced when you use natural, fossil fuels and you burn them. It's to take them and convert them into harmless gases. And so here you got nickel oxide, platinum can be pretty expensive there, but for the most part these are relatively, not going to change the price of your automobile too much, depending on what they use. But if you look here, so here we've got that's octane, a hydrocarbon, and this converter converts it to CO2 and water. CO2, carbon dioxide, we know is not harmful at all to us, right? We need it, so, and water. And so that's the point of that converter. Right here, that's the catalyst, is to convert it to something that's not harmful. Okay, carbon monoxide, we all know that's poisonous, right? So if we didn't have this converter system in our automobile, we'd have, some more accidents, I'm sure. All right, and it converts to CO2. Okay, and then this is also a pollutant, okay, and it converts it to nitrogen, which is what our atmosphere is mainly made up of, 78% anyways, and oxygen. So you can see the trend. It converts harmful gases to harmless gases. Most of the benefits of their converter system, it's obviously a much needed, part of an automobile. However, there is one drawback. Okay. When you burn fossil fuels, they produce sulfur. Okay? And so one of the pollutants, okay, is SO2. Okay? When a catalytic converter, so there's a vanadium one, but when a catalytic converter converts SO2, it takes it to SO3. Okay? Any idea why that would be not beneficial for our environment? Anybody? What's SO3 do? What could it be a precursor for? Yeah. Okay. If you, exactly, say it out loud. Acid rain, exactly. If you take SO3 and you react it with water, which water is everywhere, right? It becomes sulfuric acid and makes acid rain. Okay, so this is happening. Your catalytic converter is taking SO2 and converting it to acid rain, basically. Okay, so that's a drawback to the converter system. Yeah, and I have it right here. Yep, makes sulfuric acid, and that lead to acid rain. Do what?
Acid rain makes zombies in the 80s.
Okay. We will come back to this quite a bit. The Haber process, heard it pronounced both ways, Haber process. Okay, so we'll see this 2 or 3 times through the semester. And basically it is the reaction pathway for making ammonia. Okay. First off, I want you to notice that this is a pretty cheap way to make ammonia. What are you using? Nitrogen, which is what atmosphere is made up of, and hydrogen. Okay, so this was actually developed back in, I think it was World War I. They were trying to make explosives, and the Haber, who made this and came up with this during the war, he won the Nobel Prize actually twice, okay, because he used such cheap reagents here that you can have anywhere, and they didn't have a natural resource for making ammonia. So some places had sodium nitrate just in their natural resources, and they could convert that to nitric acid. Okay, so they were wanting this for explosives. That's what the whole point was. Okay, so you can take ammonia and you can convert it to nitric acid. Okay, we use nitric acid in setups in the lab. It is a pretty strong kind of corrosive acid, but we use it, industry. It's the precursor behind making fertilizers, dyes, explosives. Okay, and so making ammonia is very important. So it's used, like I said, all around us. Okay, and so he used a catalyst, an iron, which is pretty cheap catalyst as well, and was able to efficiently make ammonia, which then they made nitric acid, which led to explosives. But yeah, he won the Nobel Prize for this reaction. Do I? Yeah, but it's not it's not considered a reactant, so you don't have to have it on the product side, if that's what you're asking, because this is what it kind of looks like. It's a really unique process. It's actually, especially being an organic chemist, I use catalysts, but not a whole lot, but this whole idea just blew my mind, because to me, things bump into each other, they collide. I got that. I got the 3 dimensions, but a catalyst, really, to me, is kind of a miracle how they work. I'm glad they do, okay, but it's really just a surface, and my professor in college tried to explain it as a sticky surface, and that reactants want to stick to it, okay, and so here's your catalytic surface, and here we have CO and oxygen, and you have first adsorption. That means that those reactants have to be attracted to your catalyst. Okay, so there, of course, not everything can be a catalyst. Okay? Then you have the activation part, where they're sitting on the catalyst and the molecules break. So here, your 2 oxygens break apart, but they're still stuck to this surface. Then they react. So they actually react on the catalyst, and then they react and they miraculously form what you want them to form, and then they leave. Yeah, so it's a really, really unique process that's really hard to wrap your head around, of how it exactly can do that and stick to it, and I'm sure you could go into and read lots and lots and lots about it, but the main idea is that certain metals especially are sticky surfaces, so those molecules stick to them and they rearrange and you form the products that you desire, which is a pretty unique process. And as you can see, if everything leaves, you're left back with your catalyst. So a lot of times when he was asking there, your catalyst can be recovered, okay, because your products are either gases here or they're in solution, and then you can filter off your catalyst. You can reuse it a lot of times. Let's see if we have enough time for this. It won't take but a second. Okay, the last thing to talk about is a mechanism. So we're not going to get a lot into mechanism. That's organic, where we spend most of our time looking at that. But this goes back to when I told you that a lot goes on between point A to point B, or for you guys, point A to point B. For our reactants to react, there may be 2, 3, 4, 5 steps that go on in between here. Okay, the only step that affects the rate is the slowest one. So whichever step is the slowest, that's going to be the rate determining step, is what we call it. Okay, so we're only concerned with the reactants in that step, or the concentration of reactants in that step. Because if it's the slowest, so if it's got an activation energy that's really high, and all the other ones are fast, then that one's going to set the tone, right? That sets the rate for the reaction. Exactly. As fast as your slowest step will go. Yep. Okay, so here's a two-step reaction. Okay, so that dagger there, that just stands for transition state. Okay, so you have two steps. Okay, which one's going to be the rate determining step? The slow one, which is the first one, right? The first step. All right, what about this one? The organic reaction. Okay. All right, step 4 to 5. So this is what's going on. This is an organic reaction. It goes through all these intermediates here. So we're only going to be concerned with the concentration of this. Okay, it doesn't matter to you guys what that is. Okay, but that's going to determine our rate. Okay, so this one's where the very last step is what takes the longest. Okay. This reaction's just iodide catalyzed. Okay, so if you look here, you're given two steps that this goes through. So we're going to have two steps that are going to be included from A to B. Okay, we're not two, and this is the two steps. First, you take peroxide, add iodide, you form these, and then these react to form this. Experimentally, we found that rate depended on the peroxide and the iodide. Okay, so that matches up, right? Because the rate only depends on the slow step. Okay, so even though there's more steps, there could be 2, 3, 4, 5, how many ever, whichever one's the slow step is going to be the only one that the concentrations are dependent in your rate expression. Okay, here's ozone. And there's the rate law for it. Okay, ozone reacts rapidly with nitrogen oxide, produces NO2 and oxygen. And it says it's first order in each reactant and second overall. Okay, so if we were trying to determine a mechanism or steps for this, and we found this, okay, it was a two-step process. There's those two steps, ozone, we produce that oxygen, and then that reacts to form this. Okay. The rate is only dependent on our first two reactants up here because that is the slow step. Okay. And you have to experimentally determine slow and fast. So kinetics, it just gets more and more and more difficult, really, because you can actually, derive all of this and then find your, but we're not going to do that to you. So. Okay, and this would be an example of where the rate law is not consistent. Okay, so you have a slow step here where your ozone reacts, and then I know you can't really see that right there. Okay, but that's your fast step. Okay, so this proves that this mechanism is not correct. So if I tried to propose that this was what was going on in each step, and then I did a rate law, and I found, this here. Okay, then these don't match up. So our slow step is the oxygen. Okay, so this would be an inconsistent data because our slow step should be here, the concentration of the ozone. All right, on Thursday we'll practice the rate laws. So go home, there's practice under the Unit 1 tab. So go home and practice them because you will forget, even though it's just a Thursday. But practice them, bring questions, and we will spend time going through them and be sure everybody gets those. So other than that, have a good day. See you guys on Thursday. Enjoy your afternoon off. Come to class excited to be here on Thursday. Yeah, I saw that on the. Are you running in it?
Last semester I sat right there. It says, well, I'm already-
Do what now?